Hello Calc 3 and welcome back to the last video lecture scheduled for May 11th. The goal for the video is to go through section 11.5 covering areas and lengths in polar coordinates. I think I'm going to use the same format for the video that I used for section 11.4. I liked the way that turned out much more than section 11.3. So let's start off by talking about calculating area for polar curves or area bounded by polar curves. And I think it's a good idea to start by talking about area bounded by functions given in Cartesian coordinates first. So this will be a little bit of a throwback to Calc 1. So we're going to recall the method for finding the area below a curve that's given in Cartesian coordinates. So say that we have a function f of x. Just for simplicity's sake, for now, it's going to be greater than or equal to 0 everywhere, and it's also going to be continuous on this interval from a to b. Then remember that we estimate the area between our function f of x and the x-axis with Riemann sums, where Riemann sums are sums of the areas of a finite number of rectangles, like you can see in this picture here. So in this case, we have 7 rectangles. That's a Riemann sum with 7 rectangles. And to estimate the area under the curve, which is drawn in black there, we would sum the areas of the rectangles that are drawn there. And that would give us in this case, a relatively good approximation of the area under the curve. But if we want to know the exact area, is going to be given by the limit of the Riemann sums as the norm of the partitions of the interval from a to b goes to 0. If that doesn't necessarily jog your memory, a partition is just a way to split up the interval from a to b into a bunch of tiny subintervals. The norm of the partition is going to be the maximum length of all of those subintervals. So we're saying that the length of the subintervals goes to 0. And we can write the area under the curve as this expression down here. So we have the limit as the norm of the partition goes to 0 of the sum from k equals 1 to n of f of c sub k times delta x sub k. So c sub k in this expression is just some value that lies within the kth subinterval of the partition, and delta x sub k is the length of the kth subinterval in the partition. And when such a limit exists, we can actually define the definite integral with this equation here. So the definite integral from a to b of f of x dx, which we're of course all very familiar with, is defined as that limit. And I just wanted to review this because it ties in nicely with the same kind of method that we use to calculate area that's enclosed by a polar curve. So my drawing skills kind of hit the wall when it came to drawing these little sectors to estimate the area bounded by the polar curve here. So I just stole an image from the textbook. The difference here is that instead of approximating the area with rectangles, we're actually approximating the area with circular sectors. And the area of each of these sectors is given by this expression here. If you want to understand why the area of the sector is given by that expression, I would just pause the video and think about it for a second, and I don't think you'll have too much trouble figuring it out. And as we take the limit of the norm of the partitions of alpha to beta, I guess I should have said what alpha and beta were. They are listed in the picture. Alpha is down here, the value for theta below the curve in this case, I guess. And beta is the value for theta that's bounding the curve above, up here. So as the norm of the partitions of that interval from alpha to beta goes to 0, we can find that the enclosed area of the curve is equal to that limit as the norm of the partition goes to 0 of the sum from k equals 1 to n of 1/2 times f of theta sub k squared times delta theta sub k. And again, this formula looks really bad, but it's basically just taking the expression for the area that was found right here and summing all of those areas together. So moving from this expression here down to the sum actually isn't too bad. And then by definition of the definite integral, that is actually equivalent to the integral from alpha to beta of 1/2 times f of theta squared d theta. So this leads to the first important theorem of this section, something that hopefully you are already familiar with from Calc 2. So big important theorem, the area of the region between the origin and some polar curve r equals f of theta, where theta is between alpha and beta, is given by the definite integral from alpha to beta of 1/2 times r squared d theta. So this is something to keep in mind. And right after that I have an example where we're finding the area enclosed by some polar curve. In this case it happens to be a cardioid. Cardioid given by r equals 2 times the quantity 1 plus cosine theta. Again, my drawing skills weren't too great, so I just stole a graph of the cardioid from the book. And you can see after we would sketch the graph that the curve begins to be retraced when theta equals 2 pi. So this allows us to just integrate the curve from theta equals 0 to 2 pi before we start retracing stuff. So using the theorem above, the area is given by the integral from 0 to 2 pi of 1/2 r squared d theta. And then we can plug in for r using the function given above. So r is equal to 2 times the quantity 1 plus cosine theta. That gets plugged in right here. And now we can do some algebra. It looks like there's some squaring that's being done. I'm going to skip through some of the algebra until we get back down to some more interesting stuff. Yeah, so we're going to square and expand and then distribute to get to this point here. And from here, there's an interesting trig identity that hopefully you remember from Calc 2. So remember that cosine squared of theta is equal to 1 plus cosine 2 theta over 2. We use that substitution for the integral. And again, there's some more algebra that goes on until we get down here. And the integral of 3 is, of course, 3 theta. The integral of 4 cosine theta is 4 sine theta. And then there's a little bit of a u substitution that can just be kind of done implicitly for the integral of cosine 2 theta there. That gives us a 1/2 times sine of 2 theta. And we plug in a 2 pi for that expression, which will give us a 6 pi. When we plug in a 0 for that expression, we get 0, which means that this definite integral is equal to 6 pi. So the area that's enclosed by the polar curve, given by r is equal to 2 times the quantity 1 plus cosine theta, is equal to 6 pi. And another theorem, an important theorem for this section, is that if we want to find the area of a region that's bounded between two polar curves, where theta is varying from some alpha to some beta, then we're going to take the area, or the area is going to equal the integral from alpha to beta of 1/2 times the radius squared, the outer radius squared, minus the inner radius squared d theta. And of course, this is something that you should have covered in Calc 2 as well. I'm not going to give an example of it just because I want to conserve some time. If you do want to look at an example, then the book offers one. It's example 2 in section 11.5. You're free to go look at that. that'd be great. Or you could even look up some examples online if you feel the need to. I'm also going to assign some homework problems that have you finding the area between multiple polar curves. So you'll have some practice doing that if you need to brush up. Okay, so let's look at calculating lengths of polar curves now. So we just talked about areas. Now we're moving on to lengths. I first want to derive the formula for the length. So if we are given a segment of some polar curve, the polar curve is given by r is equal to f of theta, and theta is between alpha and beta. We can parameterize the curve just like I did in the previous section. So we set x equal to f of theta cosine theta. We set y equal to f of theta sine theta, where theta is varying from alpha to beta. And then we can just use the arc length formula for parametric equations that you should know from Calc 2. If you don't know it offhand, then I would go back to section 11.2 and look at it. But immediately from the arc length formula for parametric equations, we conclude that the arc length of our polar curve is equal to the integral from alpha to beta of the square root of dx d theta squared plus dy d theta squared d theta. And then using some algebra and some substitution, eventually that gets down to this second equation here. And I didn't want to put that in because I think that it'll be a nice homework exercise. I think it's exercise 29 in section 11.5. So I will almost definitely assign that for homework due on Wednesday. And this leads to the last theorem for the section. So if r equals f of theta, so if we have just a polar curve and it has a continuous first derivative, and if the curve is traced only once, you don't want to be taking, you don't want to be finding the length of a curve that's tracing back and forth over itself because it's going to be longer than it should be. So let's assume that it's traced only once as theta runs from alpha to beta. Then the length of the curve is given by this formula right here. And the last thing for this video is just an example of finding the length of a curve. So I think this is problem 22 that I just randomly selected from section 11.5. I wanted to select a problem from the homework section just so that you could look at example 3 if you wanted an extra example to look at for calculating arc length. So let's go through this example. We have the curve r equals e to the theta divided by the square root of 2, where theta is ranging from 0 to pi, and we want to find the length of this curve. So to use the theorem that's right above us here, we need to make sure that that r equals e to the theta divided by the square root of 2 has a continuous first derivative, at least for theta between 0 and pi, and that the curve is only traced once as theta goes from 0 to pi. So first off, note that e to the theta is a one-to-one function for all theta, for all real theta. So the curve is definitely sketched only once, since every output corresponds with exactly one value of theta. And it's pretty clear that r has a continuous first derivative because the derivative of r is just e to the theta divided by the square root of 2, and r is continuous. So the first derivative is also continuous. So as I just said, dr d theta is equal to e to the theta divided by the square root of 2. And so now we can use the formula given in the theorem above. The length is equal to the integral from 0 to pi of the square root of r squared plus dr d theta squared. And in this case, r and dr d theta end up being the same, which ends up being kind of nice. So now we do some algebra. There's some squaring that's done. Then we add two fractions together here. And now we get to the square root of e to the 2 theta. I guess this is an interesting thing to note. So when we take the square root of e to the 2 theta, notice that we have to put in the absolute value signs around e to the theta. So we get the integral from 0 to pi of the absolute value of e to the theta d theta. But right after we put the absolute value signs in, we can actually take them away again because e to the theta is always positive. I put greater than or equal to 0 over here, but it's also fine to put e to the theta is greater than 0 for all theta. And because that is the case, the absolute value of e to the theta is always going to equal e to the theta. So we remove the absolute value signs, and now we just get the integral from 0 to pi of e to the theta d theta. And the integral of, or an antiderivative for e to the theta is, of course, e to the theta. If we plug in a pi, we get e to the pi. If we plug in a 0, we get 1. So the arc length, all in all, is going to be equal to e to the pi minus 1. So again, if you want to look at another example of arc length, just open your book. You can check out example 3. It's outlined really well in the book. I didn't see any point in me just going through the same example that you could already get in the book anyways. So now you should have 2. And I believe that is all the content for this video, and also all the content for chapter 11. So on Tuesday, May 12th, we'll be starting up with chapter 12, which really begins the content for the course. Chapter 11 was intended to be a review that's going to be helpful when we get to chapter 15, talk about some double and triple integrals. So yeah, be prepared for chapter 12. The video should be uploaded sometime on Monday night.